So before I show you our method for calibrating log scores correctly, I thought I would try showing you another DIC example in which we might be able to improve upon the initial parameterization. Oh, and actually in this example we don't really need to, do we? I decided to try the NB10 data with the T model for the NB10 data, and we can see with our own eyes that that there are 3 parameters in that model, and with the parameterization I have, in which mu is normal, sigma is uniform from 0 to 9, and therefore not a perfectly normal distribution, and nu is uniform, again not perfectly normal, it's still doing pretty well. It says that the effective number of parameters is about 2.9, and we know the right answer is 3. Okay, I was hoping that might be an example where it misbehaved and we could improve it with reparameterization, but not so. Okay. So how does this method go? Well, it starts out just the way you'd expect, and then there's an idea that makes it work right. So the inputs to, I'm on page 39 now of section 2 of part 5 of the lecture notes. The inputs to our procedure are a data set. For example, typically a regression structure. Here's a simple data set with no predictor variables, so just a one sample data set, and a model. And the model can be parametric or non-parametric or semi-parametric, it doesn't matter. So here's a little example of a data set of 10 observations that might well have come from a Poisson distribution, and so let's see if the data are consistent with the Poisson story here. So my model is going to be that if I knew what lambda was, the yi's would be I d Poisson lambda, and then I put a diffuse prior on lambda. Let's call that model star. Well, step 1 is just what you would think. Calculate the full sample log score value for this data set, and let's say you get a number like minus 1.1. As usual with all of these methods, by themselves they don't tell you very much. Is that a big log score or a small one? Really, the answer is compared to what other model, is it better or worse? But now we're trying to do something harder, which is to say, is that absolute value minus 1.1, is that something that's feasible, is it reasonable on the basis of the Poisson model? I'm going to call that the actual log score value, ALS. And in the second part of step 1, I want to obtain the posterior for lambda given the data set Y based on this data set and that model star. I'm going to call that the actual posterior. So far we know what our log score is for our data set, and now we're going to try to figure out where that number lands in a well-calibrated comparison distribution. Step 2 goes like this. And this is the part that Gelman and his colleagues suggested doing. Pick a number M1, which is a large enough number of simulation replications to get a good idea what's going on. M1 should be a number like 1,000 or 10,000. Make a lambda draw from the actual posterior, call it lambda vi. Generate a data set of size n from the sampling distribution part of the model using the lambda you got a moment ago. And now compute the log score for this generated data set. Call that log score of I. Do that M1 times. Now you have a vector of log scores. Let's call that v.ls. Let's locate the actual log score in this distribution of LSFS values by computing the percentage of LSFS values in that vector that are less than or equal to the actual log score. I'm going to call this percentage the unadjusted actual tail area, and let's say it comes out 0.22. This is where Gelman and his colleagues would stop. They would say, you now have what they call a posterior predictive p-value, and it's 0.22, so your model's fine. That p-value is a lot bigger than the 0.05 knee-jerk place to draw the line, and so your model's fine. They actually proposed the idea a bit more generally with leaving the user a lot of different choices for what they called the discrepancy function. And here I'm using the full sample log score as what they would call the discrepancy function. Now, Milovan and I know from our own simulations and the literature that this tail area, which is attempted to be a p-value for a composite null hypothesis, namely Poisson lambda with lambda unspecified, we know from our own simulations, and we know from Jamie Robbins and that paper by Bayar and Berger, that this tail area is conservative. In other words, with the 0.22 example I just mentioned, an adjusted version of it that's well calibrated would be smaller. So we can't stop here yet. We have to do something to make it right. And so we have modified and implemented, Milovan and I, one of the ways suggested by Jamie Robbins, and we've shown that it does indeed work even in rather small samples, situations. Although our approach to implementing it is computationally intensive, and the reason is that we basically do steps 1 and 2 over and over again. So we add as a shell outside steps 1 and 2 another simulation loop, and that turns out to provide the proper calibration. So now for J, running from 1 to another number M2 that should also be a number of simulation replications on the order of 1,000 to 10,000. Make a lambda draw from the actual posterior, call it lambda star, that draw. Generate a data set of size n from the sampling distribution part of the model using the lambda star you just got. Call that the simulated data set. And now take the simulated data set and repeat steps 1 and 2 above on that simulated data set. The result will be a vector of unadjusted tail areas, because that's what you get out of steps 1 and 2. You get a tail area. The result will be a vector of unadjusted tail areas, and now you get the right answer by doing the following thing. Compute the percentage of tail areas in v.p that are less than or equal to the unadjusted actual tail area, and call that number the adjusted actual tail area. That's the properly calibrated p-value. And what we're doing basically is we're falling back on that old trick that if x is a draw from a CDF a distribution with CDF f sub x, then f sub x evaluated at x is a draw from the uniform distribution. You may remember that's a pretty standard way to generate pseudo-random numbers. You take uniform draws and apply the inverse cumulative to them, and that creates a draw from x. And we can run that the other way around. If x is a draw from f of x, then f of x has to be a uniform draw. And the reason that's appropriate is that for p-values to be properly calibrated, they should have a uniform distribution on the null hypothesis. And what happens is that the Gelman procedure does not have a uniform distribution on the null hypothesis. And we can create something that does have a uniform distribution by embedding the Gelman thing in the middle of another simulation loop that does this thing that corresponds to f sub x of x being uniform 0, 1. So we claim that this 3-step process is well calibrated, by which I mean that if the sampling part of that model really did generate the observed data, the distribution of our adjusted actual tail areas observed in this way would be uniform apart from simulation noise. So it is a legitimate p-value now. And the problem, if you're a fan of hypothesis testing and you want to understand what went wrong, what Gelman and al. Did was they didn't realize that the null hypothesis was composite. They tested the null hypothesis Poisson lambda bar, or lambda hat, where lambda hat was the actual value in the data, whereas the real null hypothesis is Poisson lambda with lambda unspecified. And so they got the p-value for the wrong hypothesis, in effect. And so to show that we're well calibrated, not that we've used enough CPU cycles yet, we can demonstrate that by building another simulation loop around our steps 1 through 3, right? Choose a lambda value of interest to you, call it lambda.sim. As k runs from 1 to m3, generate a data set of size n from that sampling distribution using lambda equals lambda.sim. Call this the validation data set, and now repeat all 3 steps of what I had before on that. And the result will be a vector of adjusted p-values. We're going to call it v.pa, and we claim that that vector is close to uniformly distributed. No, it proves that this our adjustment method is well calibrated because correct p-value should have a uniform distribution on the null, and Gelman's procedure does not, and our procedure does. And so here's some examples. Here's what you get from Gelman if the data were Poisson lambda. Here's a whole bunch of examples as n ranges from 10 to 25 to 50 to 100 to 250, looks like. And as lambda goes from 0.14 to 3.37 to 1 to 2.72 to 7.39, you will see that the unadjusted values, the ones that Gelman et al. Produce, do behave uniformly sometimes. For example, large values of lambda, their method seems to work okay. See how all those are pretty close to uniform? But for small values of lambda, especially with also small values of sample size, in fact, their distribution can be very far from uniform. The target distribution is just the flat line there that you see in each one of these. And look, everywhere you look on the left-hand side of this picture, you see things that are non-uniform, in fact, sometimes extraordinarily sharply so. Look at the cell with n equals 100 and lambda is 0.4. What's going on here is it's supposed to be uniform from 0 to 1.0. Instead, it's extraordinarily concentrated around 0.5. And so if Gelman gives you an 0.4, if it were an ordinary uniformly distributed p-value, you'd say, well, the model's fine. But look where 0.4 is in his distribution. It's actually quite far out in the left tail. And so the problem is that his p-values are not uniformly distributed, and our extra loop on the outside makes the resulting adjusted p-values uniformly distributed. So that's what's going on. In effect, what we're doing is we're referring Gelman's p-value not to the uniform distribution, but to his own sampling distribution. And by that means we figure out that 0.4 is actually quite an unusual value in this picture right here. So that's essentially what's going on. So one way to measure closest to uniformity is with histograms that are close to flat, like the ones here. Another way is to plot the quantile plot and see if it's close to the 45-degree line. And so we did that on the next page. And everywhere you look, our answers are really close to well-calibrated. These numbers are all just basically, look at it, it's all everywhere you look. Here's another one. Now we have normal distribution with unknown mean and unknown variance. And we have the sample size ranging from 10 to 25 to 50, and a whole bunch of different values for mu and sigma squared. And again, the uncalibrated version of Gelman shows non-uniform distributions. In fact, every single one of these is very far from uniform. And yet with our method on the next page, they're all pretty close to uniform. So that's how to do it. And here's some R code to do it. Now let's go ahead and run the R code. So I shall kill this off for the moment. Grab the R code from the web page. It's in this section called R code to calibrate the log scores in a simple Poisson example by improving upon posterior predicted p-values. So let's jump on that. Put all that stuff in a notepad file. And now let's get an R session. And my first note to myself is to unbuffer the output because we're going to be doing stuff over and over again and we want to watch the simulation replications. So here's a little data set at the top of this page that may or may not have come from a Poisson, but it could plausibly have come from one because look, it's all non-negative integers. And the mode is at 1, and it sort of tails off in a long right-hand tailed sort of way. It might have come from either a Poisson or from that Poisson gamma mixture I showed you before. Here I'm going to set a tolerance epsilon, and I create the logarithm of the density function for the Poisson gamma distribution, which is a gamma mixture of Poissons. This is a generalization of the negative binomial. I showed it to you many weeks ago. It corresponds to the predictive distribution in the Poisson model with the conjugate prior. So step 1 uses a prior that is gamma epsilon epsilon, so that's what the epsilon stands for in this. Step 1 goes ahead and works out the log score for our actual data set under the Poisson gamma mixture model. And step 2 places that in the context of other such full sample log score values in an uncalibrated way, the Gelman approach. And then step 3 embeds that in the steps 1 and 2 in the extra simulation loop, and that does the actual calibrating. So let's run it and see what happens. And so the looks like I returned the sample size 14, the sum of the draws, which is the sufficient statistic in this model, 29, and the log score value. The actual log score value about minus 1.71. Once again, compared to what? Is it big or small? We don't know yet. We have to calibrate it. Step 2, now this is going to be Gelman. I'll do this 1,000 times. And this part's going to go pretty fast. And Gelman says, well, that's not very unusual. According to him, the uncalibrated p-value, you would get a value like the one you got, minus 1.7, whatever that was, about 42% of the time. Now it looks like I just wrote some stuff out. So let's go ahead and read it back in and make this histogram. So here's Gelman's uncalibrated story, which show with the actual log score, and it's right bang step in the middle. In fact, the proportion of log scores, simulated log scores that are to the left of that is about 42%. All right. Now, step 3, it's going to take a while, but let's do it. And while it's percolating, we may do something else. I only asked for 100, so it's going to go pretty quickly. And as it happens on this particular one, the Gelman p-value did not actually require any recalibrating, or not much, because the unadjusted tail area was 0.416, and the adjusted version is almost identical, 0.42. So this is the distribution of calibrated tail areas, and our value we got, 0.416, is not that unusual in that distribution. So there's an example where Gelman was okay, but I showed you some pictures in which he was okay and some pictures in which he was not. Now let's generate a data set that really is from the Poisson gamma story. Actually, this is going to be from the log normal mixture of Poissons. So here we have a sample size of 10, and we generate some normal errors with mean 0 and standard deviation 0.5. And we set mu to 0, and we fill in using the mixture model that I've shown you before. Each person's lambda is equal to e to the mu plus the error, and then each person's y is Poisson, one Poisson draw with that particular lambda. So this is exactly that mixture model we had before. And this is interesting. I seem to have not put in a seed here, so there's no guarantee that we're going to get at all the same. That's interesting. We don't get the same data set. That's funny. What just happened? Oh, I see. Because I forgot to put the comment sign there. No worries. Okay, so what's our variance to mean ratio here? Pretty high, about 1.71. Let's go ahead and make a plot of the histogram. So that doesn't look much like a Poisson because it almost looks bimodal, and the Poisson can't be bimodal. So could the data have arisen from, well, it's not supposed to be a Poisson, right? It's supposed to be a kind of a mixture, but the mixture model is supposed to look sort of like an over-dispersed Poisson, and it's unusual for it to be bimodal as well. So I think we're going to find in this example that the data could not really have come from this story. All right, so step one. We get a log score of about minus 1.51. Step two. Gelman says 0.211. But his distribution isn't well calibrated necessarily. So our log score of about minus 1.51 doesn't look that unusual in that distribution. And 21.1% of the time we get values even farther in the left tail than that. And so now I'm going to do the actual calibration 1,000 times rather than 100 because I want to get a better idea what's really going on here. So I'll go ahead and run this code and we'll talk about something else while it's running. It's going to take a while to run. Okay, so back in the world of this handout here, I think we pretty well exhausted all the new stuff in it that's worth you knowing about. Let's see. All these numbers should be ideally on the order of 1,000 to 10,000, but it takes a long time to do this with big values of M1, M2, and M3. So you can pick it based upon how much time you have to devote to it and how fast your CPU is. So looking at the results I got anyway here, and it's funny, I think this code, yeah, I can see this code I wrote a while ago and didn't do a good job yesterday of polishing it. I would have preferred to have set a seed so that I get the same answer each time. The first part, I'm now back in section 2 of part 5 of the notes, and this early stuff is just exactly like what I showed you a minute ago. Here I'm getting a different data set this time than I got before, but we'll see that in my example that's here in the notes, the uncalibrated p-value was about 0.18, and the calibrated one was about half that. And so here was an example where Gelman gave an answer that was pretty sharply conservative, and we'll see what happens when we run this code. How far is it? Oh, it finished already. And oh, this is cool. The unadjusted p-value for this particular data set was 0.211, and Gelman is telling you, oh, not too much to worry about. And the correct adjusted p-value is 0.043, which is 5 times smaller. And this is why, because in the histogram of calibrated tail areas, Gelman's p-value of about 0.21 is actually pretty rare. In the world of uniform distribution of p-values, that wouldn't be all that rare, but look how rare it is in that picture right there. So there you have both a method that fails for answering this question, could the data have arisen from Model 1, namely Gelman's method, and you have a refinement to it, which succeeds in creating a calibrated, well-calibrated version of the same idea. And I commend this to your attention. If you follow the logic of my example, you'll be able to do this on models of arbitrary complexity. Okay, let's see what else is here. So I think the remaining stuff in here, let's take a moment to look at the conclusions of this part here. As we've seen some weeks ago, one way to think about the problem, solving the problem of Bayesian model specification, is to start with exchangeability judgments and have them lead directly into Bayesian nonparametric modeling. And I showed you how to do that in previous weeks, although we saw there were some significant difficulties. The code doesn't run very fast. The MCMC for it doesn't run very fast with large data sets. And also we start getting these strange posterior distributions that are very lumpy sort of behaviors, and we don't really know why. I should tell you that as part of getting ready for this week, I took the NB10 data, which you recall is rounded to the nearest integer, and I jittered it by adding noise to it to make it much more continuously behaving on the real line, and I got the same kind of nasty posteriors with those weird lumpiness in the one for mu and sigma that I showed you before. Then I created a data set with 1,000 observations that was simulated from a T on 3 degrees of freedom. So I tried to give the Bayesian nonparametric story a lot more data to see what would happen, and it still produced really lumpy, weird-looking lumpy posteriors for the parameters. And so this is something where I came into this course being prepared to recommend Bayesian nonparametric methods to you more enthusiastically than I leave this course doing so, because I just don't believe those posteriors as an accurate reflection of what we do and don't know about those parameters. So that's something I'm going to have to clear up from in my own work, and when I do, I'll try to send a message out to all of you or put something back on the web page. I'm going to leave the web page up indefinitely for this course so that anybody who stumbles upon it, or maybe I'll advertise the web page, and people can so I'm going to continue to grow it. I'll put stuff on it that clarifies things as I continue to learn them. So Bayesian nonparametrics is one way to avoid the dilemma posed by Cromwell's rule. You remember, I think I told you about that a long time ago. Cromwell's rule says anything that you put 0 prior probability on has to have 0 posterior probability, no matter what the data looks like. Similarly, anything you put prior probability 1 on has to have posterior probability 1, no matter what the data looks like. And so, as a general matter in the Bayesian paradigm, you want to try really hard not to put prior probability 0 on anything that might remotely turn out to be real, true, because if you give it prior probability 0 and you don't give yourself an opportunity to go back and change that prior, you will never learn that it was non-zero, because the posterior has to be 0 on it. And an example of that would be in model space. If you put all your eggs in a Gaussian basket and the data have a bimodal character, the bimodal distribution has prior probability 0 under the Gaussian sampling story. You can't get a bimodal distribution from a single Gaussian. And so the Gaussian model is always going to give 0 posterior probability to the data if the data are bimodal. And so that's nasty. So we either need to come up with a way of not giving 0 prior probability very much across model space, which is what Bayesian nonparametrics tries to do, or we need a way of going back and noticing that our original prior in model space had too many zeros in it, and we need to go revise it. And that's what calibration cross-validation does for you. It allows you to peek at the data and fiddle about with the data, but pay the right price for having peeked and fiddled. So, like it says here, BNP is one way to try to avoid the dilemma posed by Cromwell's rule. Calibration cross-validation, the name I'd prefer to use now, is another. Third point, model choice is really a decision problem and should be approached via maximizing expected utility with the utility structure that's sensitive to real-world context, but that's hard work. When the goal is to make an accurate scientific summary of what's known about something, the predictive log score, the one I've shown you, LSFS, has a sound generic utility basis and can yield stable and accurate model specification decisions. DIC can be thought of as a fast approximation, it turns out, to the cross-validation log score, but it can behave unstably as a function of its parameterization, getting those p hat d values like minus 66 and minus 80 and so on. That was embarrassing. The full sample log score is a lot faster than the cross-validation log score, and it has better small sample model discrimination power than either the cross-validation approach or DIC. And so that is one of my two favorite ways of comparing models from the Bayesian point of view. Full sample log scores and BIC when it's available. But of course, it's not always available because you have to be able to actually stare at the model and count the parameters, and that doesn't include random effects models. Generic Bayes factors are highly unstable when context suggests diffuse prior information. Many methods for fixing this have been proposed, most of which seem to require an appeal to ad hocery that's absent from the full sample log score approach, but at least BIC prevents you from the worst of your excesses in having to deal with the issue of diffuse priors. The basic Gelman et al. Method of posterior predictive model checking is badly calibrated. When it gives you a tail area of 0.4, the right answer might be 10 times or even 100 times smaller than that. And Milvan and I have figured out a way to fix that by putting that extra simulation loop outside. So that finishes part 2 of section 5. And we're now back in the world of part 1 of section 5. And I did want to say a little bit more about callback library. I've been referring to it on and off this course, and I realized I didn't do a very good job of explaining to you what is going on in it. So let me take a minute to talk about callback library. So can that be seen in the back of the room, big enough to be able to read? I hope so. Suppose you have a strictly positive density, P of y, on the real line, in particular over some interval, capital I, on the real line, and you have found a way to approximate that density, and you're wondering how close the approximation is to the truth. And so you found some other strictly positive density, F, on that interval. Then a natural question that arises is how far is F from P? And Solomon Kullback, and I forget what Leibler's first name was, back in the early 1950s, showed that the best way to measure the discrepancy, and they called it the divergence between F and P, is through what we now in their honor call the Kullback-Leibler or KL divergence of F from P. And you'll notice that this idea is asymmetric because P is the right answer and F is the approximation. So when we write delta for the Kullback-Leibler divergence of F from P, you see F given P, it's as though we know that P is the right answer, we're wondering how far F is from P. Another way to write it is KL, open parenthesis, little f, double vertical bar P, close parenthesis. So that's somehow the Kullback-Leibler divergence of F from P is the way people read that out loud. And what they showed was that the best way to work that out, that measure of, it's not yet a distance measure because you know distances have to be symmetric. And we'll make it symmetric in a little while, but it's partly a distance. It's something that can easily be made into a distance measure, and instead we'll call it a divergence. What you do is you work out the following integral. P log P over F, that's the right integral. That measures how far they are apart in the optimal way. Now what is that? Well, log P over F is the same as log P minus log F, and they're both multiplied by P. And so it's actually the difference of two integrals, namely P log P minus P log F. But look, P of y is a density in each case. F of y might not even be a density. It's just some, oh no, F of y is supposed to be a density also. But in any case, P is a density, and so we have something or other times P integrated, so that's an expectation in disguise. It's the expectation, the first term is the expectation of log P with respect to the P, this density, and the second term is the expectation of log F with respect to the density. So Kullback-Leibler divergence is actually the difference of two expectations. One of them is the expectation of log P with respect to P, the right answer. The other one is the expectation of log F with respect to P, where F is the approximation. Now, if any of you are information theory people, you should recognize the expectation of the logarithm of a density with respect to itself as having something to do with entropy. And so actually, they didn't write about it in their paper in 1951, but they were actually just figuring out independently from Claude Shannon, who invented the entropy idea back in the, just a few years before, actually, 1948. They were actually just inventing a kind of relative entropy, the comparison of the entropies of each of those two distributions. And so, like it says here, this is directly related to Mr. Shannon's idea of the entropy of a distribution. We can talk about this most readily in the discrete case. If an unknown quantity y takes on a finite number of distinct values, little n, let's say, with probabilities p1 through pn, then the entropy of the distribution is defined to be capital H of the vector p1 through pn, simply minus the sum as you go across all the values y can take on of pj log pj. And once again, since pj is a density, a discrete density, this is the expectation of the log p's with respect to p. So look, minus expectation of p log p, that's the entropy. But a minute ago, we had two things that look just like that. So each of these is an entropy, and one of them is subtracted from the other. This is the entropy of one of them minus the entropy of the other, because minus minus makes a plus. And so the Kullback-Leibler divergence is just relative entropy in disguise. The Kullback-Leibler divergence of F from P is equal to the entropy of F with respect to P minus the entropy of P with respect to P. And I've defined that in the following way. It's natural to extend the definition of H as follows. Let's call the entropy of F with respect to P, where each of them is a vector of probabilities, strictly positive numbers, as simply the minus the expectation of log F with respect to the distribution P. And of course, that's asymmetric in F and P, but you can symmetrize it just by doing it in both directions and averaging, right? So that'll symmetrize it without any trouble. If you need an actual distance measure, then that succeeds at that. So that's my attempt at being a little clearer about what the Kullback-Leibler story is. And in fact, if you think about things from that point of view, log scores directly have a Kullback-Leibler interpretation, like it says here on page 58 of section 1 of the part 5 lecture notes. Let's work out the Kullback-Leibler divergence of the predictive distribution with respect to the actual data generating distribution, and then we'll approximate the data generating distribution with the empirical CDF of the data. So the left-hand side of equation 26 is the Kullback-Leibler divergence. And when we expand that out in terms of those two entropy terms, we see that the first term, expectation of log data generating model with respect to itself, is constant as far as the thing that we are trying to learn from the data. And so it's irrelevant to the process of trying to learn the predictive distribution from the data. And the second term is the expectation of the log predictive with respect to the true data generating density. And if we approximate that with the empirical CDF, you get equation 25 right above there. Because the way you take an expectation with respect to the empirical CDF is you give weight 1 over n to each of the data points y1 through yn and average. And so basically what we see from this equation 26 is that minimizing the Kullback-Leibler divergence between the predictive and the true data generating model is approximately the same as maximizing the full sample log score. And so that's another way that you can see that full sample log scores are a good thing to do. Now, I have a bit of material here comparing BIC on the one hand with log scores on the other hand. And to pin this down even more vividly than we did last week, I want to make another chart that draws a bright red line between the two tasks that each of these approaches is trying to do and the resulting behavior of each of these tasks. So over here we have as our goal good out-of-sample prediction. And over here we have consistent model selection. And I'll redefine that for you in a moment. In fact, let me do that on the next page and come back. Page 15, page 16. Okay. A method for choosing between Model 1 and Model 2 is consistent if probability it chooses Model 1, given that the data generating model is Model 1, you'd want that probability to be what? Big or small or in between? When Model 1 is the right answer, you'd want the probability that that method chooses Model 1 to be big. if that probability goes to 1 as n goes to infinity with the ensemble of models that you're comparing consisting only of the models M1 and M2. You're not allowing the model space to be enlarged based on more and more data. So it's consistent if that's true, and also following is true. If A is true and also B, the probability that it, again, whereby it means a method for choosing between models, it chooses M2, given that the data generating mechanism is M2, that also goes to 1. So in other words, whichever model is right, you have a consistent model selection method if no matter which model is right, the amount of posterior probability that it lumps on that model goes to 1 as you get more and more data. And that definitely sounds like a reasonable thing to want. But the problem with that, there's several problems with that. Here's problem 1. You don't have n equals infinity, comma. You have, e.g., n equals 418. And so what happens at n equals infinity, unless it bears directly on n equals 418, is irrelevant to you. Moreover, as n increases, I think we've talked about this before, and I'll come back to it again in these PDF notes. What will you as a modeler want to do as you get more and more data to be able to do a better and better job of at least describing the complexity that you see in your data set? Are you going to want to stick with M1 and M2 and you're going to want to make that model ensemble grow, and you want to fill it with models that are of increasing complexity as n increases? So this is a bogus asymptotics because it's a fake asymptotics in which you just keep model 1 and model 2 as your only models you're comparing, and you let n go to infinity. But that's not how people actually work as scientists. You want the ensemble to grow. And no one knows how to do that asymptotics. No one's done that yet. Because it's hard to build an asymptotics in which the model ensemble grows in a way that mimics how good scientists actually have things grow. It's been hard. People have found it hard to quantify that. So as n goes to infinity, you want script m to get bigger, not stay fixed. And by bigger, I mean you want to add more complex models to the mix. And so that's bogus asymptotics. And I think I told you guys last time that a guy who believes a lot in consistency is Jim Berger. He was, last summer he came and gave a week-long set of lectures at Santa Cruz, and I was invited to be the discussant on several of the days of his lectures, and we got into a good old discussion about this point. I wish I had been able to come up with the following counterexample to his desire for consistency at the time, but it only occurred to me later on. And again, I'm repeating myself, those of you who were here last week. Berger says he won't ever use a method that's not consistent in this sense here. In other words, he won't use a method that misbehaves at infinity, according to this particular asymptotics. So now let us examine Professor Berger's attitude with respect to taking aspirin when he has a headache. Eating an infinite number of aspirins is an example of misbehaving at infinity with respect to the process of trying to get your headache to go away with aspirin. Although, as you pointed out last time, it actually does make your headache go away. It just makes it go away permanently. I want to know how well my method works with 2 aspirins. That's my sample size for aspirin. How well does my method work for n equals 2 aspirin? And being told that it misbehaves at n equals infinity, which is what Berger is claiming is all that matters for a criterion, tells me absolutely nothing about how well it works with n equals 2. Doesn't that seem, I mean, I don't see how it's easy to rebut that. That's my position on consistency. It sounds like a nice idea, but it's based upon bogus asymptotics. Now, having said that, there are a bunch of people in the world who still think it's a good thing to try for. I haven't tried my aspirin argument out on all of them. In fact, I haven't even had a chance to try it out on Jim Berger. So, Jim, if you're listening to this for posterity, I'd love to have a couple of beers with you and talk it through. How about a couple of aspirins? Yeah, exactly. After we've shouted at each other for a while. So Bayes factors turn out to be something that's way in this world here. They always try to achieve consistent model selection. And a special case, as a special case, we have BIC. And as I've told you, I like BIC when you can implement it. Can't always use, e.g. when can't count number of parameters in the models you're comparing. Over here on the good out-of-sample prediction side, we have AIC, DIC, and full sample log scores. And there's a direct progression. For me, there's a direct progression from the general idea of Bayes factors to the specific of BIC in the direction of better, because, as I've told you, BIC does not even allow you to mess about with the prior distributions on the parameters inside each model. It basically dummies them out of the calculation in a way that makes sense to me. It's that unit information prior idea. DIC is better than AIC because it works with hierarchical models. Hierarchical random effects models. And for my money, full sample log scores are better than DIC because DIC misbehaves in counting the number of parameters, and it only works for parametric models. So those are my 2 criteria that I recommend for your general use. BIC when you can use it, when you can actually count the number of parameters. Full sample log scores works all the time, any model. But the consistency thing I need to tell you about is that the following. When you're comparing 2 models that have different dimensionalities, BIC, and you can count the number of parameters, BIC is consistent at both models. When you're comparing models that have different dimensionalities, full sample log scores are only consistent at the more complicated model. They're not consistent at the simpler model, and that's because they were tuned to come up with good out-of-sample predictions, which is not the same tuning as trying to be consistent. So let me say that again, because it's an important distinction to keep in mind. So I'll give you a really simple example that is often irrelevant to actual statistical practice. model 1, yi, iid normal 0, 1, I equals 1 to n. In other words, you're in a Gaussian and you know the variance and you even know that the mean is 0. So these things are both known. Model 2, yi given theta, iid normal theta comma 1, theta given some prior, for example, diffuse. Now, the variance is known, but not the mean. These models have different dimensionalities. The dimension of model 1 is 0, the dimension of model 2 is 1. There aren't any parameters in the first model, and there's one parameter in the second one. Bayes factors, comma slash BIC, probability BF slash BIC chooses model 1 given that model data generating equals model 1 converges to 1. That's the consistency I talked about as n goes to infinity with the ensemble fixed at M1 and M2, inappropriately fixed there. Similarly, the probability that Bayes factor slash BIC chooses M2, given that MDG equals M2, goes to 1. They were designed that way. Log scores, though, LSFS, have a slightly different behavior as follows. Probability LSFS chooses model 2, given that model data generating equals model 2. And by the way, I should say what I mean by that. Model 2, when I say model data generating equals model 2, what I mean by that is that the second line of model 2 is, quote, true for some value of theta. In other words, we're putting all our money on that particular family, but we don't know what theta is. And the data generating model being model 2 means that it has exactly that form there for some theta. And what will happen is that the Bayes factors will find that out and find the right theta. Okay. So will log scores. When MDG equals M2, this still goes to 1. But watch this. When MDG equals M1, the probability that LSFS chooses M2 still goes to 1. That's what happens with log scores. In other words, even when model 1 is right, as more and more data accumulate, log scores choose the more complicated model. And they do that because they were built to create good out-of-sample predictions, and you just have to have more complicated models to do a good job of that. Now, why doesn't this bother me? Apart from the fact that the asymptotics are bogus and the fact that I won't really have infinity observations, the other reason it doesn't bother me is that most of the time, so you can see that model 1 is a special case of model 2 where you somehow know that theta is exactly equal to 0. Model 1 equals model 2 with theta equals 0. But when you're in a situation where your uncertainty about theta is continuous, as is almost always the case, then what's your prior probability that theta is exactly equal to 0? 0. And therefore, what's your posterior probability that theta is exactly equal to 0? 0. Therefore, when your uncertainty about theta is continuous, Model 1 should never even be compared with Model 2 because we know Model 1 is wrong. You have to learn theta from the data. Whatever theta is, it will equal 0 precisely, point mass on 0 with probability 0. And your job, instead of trying to figure out whether Model 1 is right or not, is to realize that Model 1 is irrelevant when your uncertainty about theta is continuous. And no wonder log scores always go to Model 2 because it's the only right model when your uncertainty about theta is continuous. So when your uncertainty about theta is continuous, Model 1 is bogus. And I'm actually delighted that log scores turn their back on the bogus model because we know already that theta is not 0. There will, from time to time, be actual problems you encounter as a scientist in which it does make sense to single out a single number on the number line as representing the right answer under some theory and other numbers than that singleton corresponding to the right answer under another theory. And I gave you the only example in 35 years of applied work, I gave you last time the only example that I've ever encountered that way. It involved that story about the T machine at UCLA. Those of you who were here probably remember that. Those of you who were not, shall I say it again? It's a good story, and then we'll go to lunch. I used to work at the Rand Corporation, then I went to UCLA. For some reason, I used to like to drink a lot of tea in those days, and for some reason, the machinery for making tea got lost in the move or something. And there was about a month at UCLA when I didn't have any way to get tea except to go to this machine that made this thing it called tea anyway. So you put in a quarter, and out comes a nasty little plastic cup with the brown liquid in it that they called tea. Have I related to you Abraham Lincoln's joke about coffee and tea? Yes. Okay. So same idea. So all right, now I have this cup in front of me, and I am drinking it and looking at the machine, and there's a label on the outside of the machine, not laminated into the plastic of the machine, but stuck on as a paper label with a stickum on the back of it, just put on next to the slot where you put in your quarter, and it says something like the following. You may be lucky. Next time you put a quarter in, you'll get your tea, but we're going to give you your quarter back. We might give you your quarter back also, implying the existence of a randomization device inside the machine that would every now and then give you a free cup of tea. All right, so I kept track. It was interesting. I kept track. And 78 consecutive cups, I didn't get a free cup of tea. So my model here is that the yi's are I-D Bernoulli theta. So here's my model, yi given theta, IID Bernoulli theta, I equals 1 to n. And under theory 1, I started to wonder. I said to myself, you know, these people might have worked out that it was a lot cheaper to put that label on the outside of the machine and not put in any hardware inside the machine that actually did any randomizing than it was to put the hardware in there. And so under theory 1, there is no randomization device inside the machine, and that therefore, apart from things going wrong, like somehow their little machine made some other mechanical malfunction and gave me the tea and the quarterback, under theory 1, theta is exactly equal to 0, and it corresponds to the real-world theory that there is no randomization device at all. RD for short. Theory 2 says that there is an RD, and that theta is some number that's positive but probably close to 0. They would have an incentive to keep it small because they don't want to give away too much free tea. But they also would have an incentive to make it big enough that every now and then someone would get a free cup of tea, maybe making them come back to the machine more, for example. That, in 35 years of applied work, is the only example I've ever found where it was worthwhile to what amounts to test a point null hypothesis that a parameter is exactly equal to some value like 0. That's my only example in 35 years. Now, Berger lately pointed out that before they found the Higgs boson, you could maybe fit that into this framework, because either there is no Higgs boson, which is like saying some parameter that measures how strong its effect is on the world is exactly equal to 0, or there is a Higgs boson and its actual strength parameter is something other than 0. But even there, that's a little bit tenuous, because what they seem to have found so far is possibly not the Higgs boson, but a Higgs-like particle. And so that represents some sort of continuum of things that are Higgs-like, in which case we're not back at point mass at 0 anymore. We're back at trying to estimate some continuum of things that are Higgs-like. And so do you see the central distinction I'm making here? I think it's silly in almost every example I've ever seen to test a null hypothesis that some parameter is exactly equal to 0 or exactly equal to 14 or exactly equal to anything else. Instead, my interest is in, whenever my uncertainty about that thing is continuous, my interest is in estimating how big it is, not testing whether it's 0 or not. If I know for sure it's continuous, my uncertainty about it's continuous, then my interest is always about finding out how big it is, not asking whether it's 0 or not, because I know already that it's not 0. Did you have, yes, Tony? Well, okay. Suppose we look at Newton and we embed Newton in general relativity. Then Newton is probably a special case of general relativity in which something has been set to something, for example. That shows that instead of testing whether Newton was right, what we should be trying to do is to find a model that includes Newton with something that varies smoothly, and once we get away from the value that leads to Newton, we are at a better model. And so where I'm headed with that is that 300 years from now, we'll probably know that special relativity is wrong also, because it was a special case of this bigger thing that's right, and it involved expanding with respect to some continuous parameter again that used to be set to some value that hard set by Einstein to some value. I really have trouble, other than my T machine, I really have trouble finding any problem I've ever seen in which your uncertainty about something had an all or nothing character that corresponded to a parameter exactly being equal to a value. And it's time for lunch. You can think about this and come back and bombard me after lunch with examples where you know that that is what's going on for you. So VC Ops, we're going to stop now and start again at 1:30.